Okay, so now our next presenter, Dr. Christian Schyr from AVL Germany. I'm happy you're here. We know each other, I think, 5 or 6 years now. You are principal engineer at the Advanced Solution Lab of AVL Germany in Karlsruhe. Your main interests are new development methods and tools for highly automated and electrified mobility systems in the automotive, agricultural and maritime domain. I remember we talked a lot about chips the other day. You authored over 100 scientific publications. You have 8 patents. Your PhD is from the KIT. You also have a degree in aerospace engineering from the University of Texas at Austin. And last but not least, a diploma in mechanical engineering from the Vienna University of Technology in Austria. So we are really happy to have you here. We are looking forward to your presentation and the discussion afterwards. So I give the word to Dr. Christian Schyr.
Okay, thank you very much, Dr. Fischer. Hello and welcome to my talk. I have the honor to present you a new project. It's a project with organizations, research organizations and companies strongly supported by e-mobil Baden-Württemberg. Thank you very much. The project called KISSME. So KISSME is essentially the German name of the project, and as you can see in the announcement, I hope in the next minutes I can give you a more deeper understanding what this project is about. So the project started beginning of this year. It's planned to last for 3 years, and the funding to be mentioned is done by the German state, by the Ministry for Economy, and it's in the funding program New Vehicle and System Technologies. So, to introduce the project, what is the main motivation for project KISSME? First of all, automation is a hot topic, not only in automotive industry, but also in different related industries like shipping mentioned by Dr. Fischer, but also aerospace engineering. Consider the upcoming drone industry, also now a hot topic in Germany. So when we look at such a scenario, especially in dense urban areas, automated vehicle must make reliable decisions under any conditions in real time. So real time means if we detect a critical scenario, and I will come back to that later, it must be detected reliable in a given short time period. So what's the big challenge now? As you can imagine, such scenarios in urban areas, they have a lot of traffic participants. Not only that, all of them are related somehow to infrastructure. So to capture that and to get a good understanding for the software decisions to be made for a safe and reliable driving of different vehicles in such environments, a wide range of sensor sets has to be used to capture the surrounding environment. So we have to scope with a fairly huge amount of data coming in from all the different sensors, like camera sensors, like radar sensors, like LiDAR sensors. This is an example what I mean with critical and relevant scenarios. So first of all, a critical scenario is really where it's getting dangerous. So you know from your driving in everyday situation, suddenly someone steps in front of your vehicle, wants to cross the road unexpected. You have to take a fast and strong decision to avoid any accidents. Relevant scenarios are some things which are not immediately lead to an accident, but they're critical in such a sense that it might be that some sensor data getting degraded, we call it. That means the sensor does not provide the full reliability we see, for example, under favorable weather condition. Like when we look outside now, we had even snow now in April here in southern part of Germany. So we have to have a really reliable understanding of the environment of our sensor set. Another issue comes with that is different traffic configurations, not only in urban areas like construction sites, but also in rural areas, like when we have automated vehicles on the road, for example, to transfer from a farming location to a farmyard, and then suddenly they are confronted with people driving fairly fast on electric bikes on narrow roads. Or when we have situations where we're driving on hilly and curvy roads, so that our environmental perception, we call it, has to be excellent under all these conditions, so that we are capable in the future to provide reliable automated systems. This is an example, and also the current challenge in not only in our group, in the consortium of the KISSME project, but also in the overall industry, working hard to increase the reliability and robustness of autonomous systems. So this is one of our test vehicles in the project, which has a fairly, I would say, moderate sensor set. It has 6 cameras to get a 360-degree view around the vehicle. We have 3 LiDAR systems, which is not too many. Yeah? We have 1 precise location, and we have abundant conventional vehicle systems like wheel speed, steering angle, and so on. And just as an example, with this vehicle, as soon as we start recording, we generate around 360 megabytes of raw data every second. So when you calculate it up and say, well, I'm driving 1 shift with 1 set of driver, yeah, then we're generating 10,000 gigabytes in 1 shift. That's a really huge amount of data. No? And every gigabyte, every terabyte, every petabyte, we keep on later on for later processing getting more and more expensive. Yeah? And so the current challenge is, how can we reduce this kind of big amount of data to this amount of data which is really useful and valuable to be processed and stored for later analysis. So coming back to our project consortium, we have a fairly balanced aggregation of research organizations like KIT, like Fraunhofer EMI in Freiburg here in Baden-Württemberg, like Research Center Informatics in Karlsruhe, working tightly together with industry. We have a large industry with Bosch Research, we have a technology provider EWL, where I'm working for, and we have 2 small and medium enterprises, LinkDAO, MindMotive, and not to forget, actually there are 3 ones, also EWA Consulting. One unique configuration in our consortium is a very strong support of so-called associated partners, which are ESAM, I will come back later for standardization, and e-mobil Baden-Württemberg as our cluster. So, what are the project goals? We have 2 main goals. One is onboard. I will explain in a minute. That means what happens on the vehicle. And this is essentially focused around the question, what shall we record, what shall we store, yeah, for later analysis? And the related question to answer, what can we do off-board? That means in the office, having the data in the cloud, to analyze data and improve our intelligent algorithms to be implemented on board. So this is the key challenge, not only for the onboard system, but to have a parallel process, a parallel structure to improve continuously the detection of critical and relevant scenarios. I will give you now a practical overview of one of our planned vehicles. You see here, this is the onboard unit. That means we have on the lower side the incoming data from control units, conventional speed sensors, acceleration sensors, but also the wide range of data coming in from environmental sensors. As I mentioned, camera, LiDAR, radar. So all of this has to be processed, adapted, brought into efficient data formats until it's passed over on board to our new components, to our AI-based components. And they have essentially 3 main functions, which are the object detections. So which objects are around the vehicle. We have the understanding what are these objects doing and what are the planning to be, so that we can derive so-called scenarios. And within the scenarios, we can derive so-called maneuvers, so that we know what are the different activities of the traffic participants in this situation, so that we can have a sound decision, is this a critical, a relevant scenario or not, and take the appropriate automated measures to process this data or not. One big issue, not in our project, but also in the overall industries, we have to work together within different companies, between OEMs, between Tier 1, between technology providers, between tool suppliers. And the key to success here is standardization, not only in Germany, but all around the globe. And Germany is very active, especially in the ESAM group, which is a non-profit organization working hardly to improve existing standards. These are the so-called OpenX family for automated and autonomous driving, but also continuously coming up with new standards which support the development and the production of highly automated vehicles. In our project KISSME, we not only want to work on algorithms, on function, we also want to prove that that can work. So it's not a fairly scientific-oriented project. It also has a strong practical focus, where we have 4 different groups of demonstrator vehicles, not only on the road yet, but also continuously improved with the upcoming extensions and add-ons for our AI-based algorithms. This is a classic passenger car you can see, provided by Research Center Informatik. This is a so-called people mover, a small bus, an unmanned bus, no driver, just a safety driver currently, in the future hopefully non-safety driver necessary, provided by Bosch Research. We have a commercial transporter provided by Karlsruhe Institute of Technology, and we have a commercial utility vehicle unmanned provided by AVL, where we want to implement, demonstrate and evaluate our project results. So I'm coming now to the summary and outlook. I showed you the basic challenge for collecting and handling large amount of data for highly autonomous vehicles, and the focus of our project KISSME to come up with new AI-based algorithms and functions within an efficient architecture, utilizing existing and upcoming standards to support an efficient development of such vehicle concepts, but also to bring a significant contribution to the successful introduction into daily lives. Thank you very much, and I'm glad to answer any questions.
So, thank you very much for the presentation to Christian Schyr. Actually, as we have a few minutes left, one question which comes to my mind, I think the KISSME project is very interesting approach. We're always discussing about in artificial intelligence that we are somewhere there's a large distance between Europe and China and North America, and a lot of people are talking about certain European way in artificial intelligence. What's your opinion, or what's the point of the project on this way?
Well, I always say there's a big difference between the different systems. When you look in Europe, we have a system where we want to do as much as possible before we go on the road, before we bring vehicle systems on the road. So we have to do a lot of effort to secure, to have a really high level of security, of safety. When you look at other countries, like in North America, it's much more easier to bring systems on the road, but if something happens, you have to take, you are accountable for that. Okay. Yeah? So that means you have to make insurances and so on and so forth. And this, I think, is system immanent. So in one system, it's easier to get on the road, but if something happens, you really have to pay a lot of money. In Europe, we have to make a lot of effort upfront, yeah, so that hopefully nothing happens. There's one issue I didn't explicitly mention, which is privacy. If we have cameras on board, we are obliged to 100% fulfill the actual legislation, which also is one strong focus in the project, to have more efficient algorithms that we do not even take critical data off the vehicle. So we do not even store them on the vehicle. So data privacy, to scope with it with significant cameras is expensive, and we want to take that into account, and this is also one benefit to research in the area of more efficient algorithms to process the data already on board, be it for research purpose, but also later on when vehicles go into production, that we have a kind of event recorder and so on, also using these algorithms.
Yeah, thank you very much. I think we can go a little bit deeper in the panel discussion afterwards. So for the moment, thank you very much to Christian Schyr from AVL Germany.